What would it actually take to live to 150? 4 videos ago, we asked why we age. We found shortening telomeres, senescent cells, corrupted genetic instructions, and species that evolved ways around these processes. Aging is not random. It follows biological mechanisms, which leads to a more specific question. What would actually need to change for a human to reach 150 years in good health? The answer is more concrete than most people expect, and the list is shorter than you might think. Start with the people who already achieve a part of it. Around the world, there are hundreds of known supercentenarians, people who reach 110 years or more. They do not get there through experimental therapies. They get there through biology, and when researchers study them, a remarkably consistent pattern appears. Supercentenarians do not simply live longer, they delay disease. The conditions that kill most people at 75, cardiovascular disease, cancer, diabetes, and neurodegeneration, often appear only in the final years of life. A 105-year-old supercentenarian is not a fragile 75-year-old who survived longer. Their biology, in many measurable ways, remains younger than their age suggests. They often carry genetic traits that reduce chronic inflammation, maintain immune function, clear cellular damage more effectively, and protect against multiple age-related diseases at once. This reveals the first clue about reaching 150. It will not come from one miracle intervention. It will require a combination of strategies, each targeting a different mechanism of aging and strengthening the others. In 2013, researchers created a framework to organize the biology of aging. They called them the hallmarks of aging, a set of biological processes that explain what happens inside an aging body. The original list contained 9 hallmarks, later expanded to 12, but 5 of them reveal much of what we have explored in this series. The first is genomic instability, the accumulation of DNA damage that repair systems cannot fully correct. The second is epigenetic alteration, the gradual corruption of the biological instructions that control gene activity. The third is loss of proteostasis, where cells become less capable of building and clearing proteins, allowing damage to accumulate. The fourth is cellular senescence, the buildup of harmful zombie cells that disrupt surrounding tissue. The fifth is stem cell exhaustion, the decline of the regenerative systems that maintain and repair the body. These processes are not isolated. They form a connected network. Senescent cells damage their environment. Exhausted stem cells slow repair. Damaged proteins increase cellular stress, accelerating further decline. This is why aging cannot be solved with one simple intervention, but it also reveals an opportunity. Targeting multiple hallmarks together may create effects far greater than changing any single process alone. Here is what that looks like in practice, and what already exists. Senolytics are drugs designed to remove senescent zombie cells that build up with age. They are already being tested in humans, with early results showing effects similar to what researchers observed in animals. They are not transformative yet, but they represent a real attempt to target one of aging's major drivers, cellular senescence. Rapamycin, originally developed to prevent organ rejection, targets the mTOR pathway that controls how cells use resources. In mice, it extends lifespan even when treatment begins later in life. Human studies are exploring whether related compounds can improve immune function and other aging processes. NAD+ boosters such as NMN and NR aim to restore declining cellular energy systems and are being studied for their effects on biological aging. Partial epigenetic reprogramming, a biological reset that attempts to restore younger cellular states, has also reached early human safety trials. Stem cell therapies are advancing as well, with the goal of restoring the regenerative capacity that declines with age in tissues like muscle, blood, and skin. But none of these approaches is the answer alone. Each targets only part of aging's complex biology. Reaching 150 years in good health would likely require several strategies working together, repairing damage faster than it accumulates year after year, not immortality, not defeating biology completely, simply keeping the balance shifted toward repair for far longer than we can today. There is a concept in longevity research called longevity escape velocity. The idea is mathematical rather than biological. If science can extend healthy human life by more than 1 year for every year of research, a threshold is eventually crossed where the interventions keep ahead of the aging. The person receiving them does not outrun death. They outrun decline. Whether we are close to that threshold is genuinely contested among serious researchers. The honest answer is that nobody knows. The biology is progressing faster than most predicted a decade ago. The distance between where the science is now and what 150 would require is real and significant. The gap may close. It may not close in time for most people alive today. Here is the honest part. The biology may be one challenge. It may not be the hardest one. Longevity therapies will not arrive equally. Early access will likely follow the same pattern as other expensive medical breakthroughs, meaning the first beneficiaries may be determined more by wealth and access than by need. That is not a reason to stop the research, but it is a reality that must be addressed before the technology arrives. And longer lives will reshape society itself, retirement systems, careers, inheritance, housing, relationships, and politics. Extending human lifespan may be a biological challenge, but adapting society to 150-year lives could be the greater one. We started with a checklist: the hallmarks of aging, possible interventions, and the gap between current science and the goal of extreme longevity. That gap is real. The progress is real. Whether they meet in time remains unknown. But beneath the science is a deeper question this series has been asking from the beginning. Not only whether we can reach 150, but whether we should. And what a world beyond natural death would truly mean. That is where we go next.